Imagine a machine so small it fits in your hand, yet powerful enough to challenge the limits of reality itself. Not theory, not speculation, reality. In December 2024, a quantum chip called Willow solved a problem in under 5 minutes, a problem that would take the most powerful classical supercomputer 10 septillion years to complete. That's not just faster. That's breaking the scale of what we thought computation even was. And when physicists looked closer at the numbers, something didn't add up. Not metaphorically, physically. Because the resources required to perform that calculation don't seem to exist within a single universe. So the question is no longer, how fast is this chip? The real question is, where is the computation actually happening? When Google revealed Willow, the headline focused on speed, 5 minutes versus 10 septillion years. But speed is the least interesting part of the story. The real anomaly lies in scale. That number, 10 septillion, is so absurd it stops being meaningful. It's not just beyond human time. It's beyond cosmic time. Even if every computer ever built had been running since the beginning of the universe, they wouldn't finish the task. Yet Willow did. This isn't like upgrading from a bicycle to a jet. This is like jumping from Earth to somewhere outside the map entirely. Previous quantum chips like Sycamore already hinted at this direction, but there was always debate. Maybe classical computers could catch up. Maybe the gap wasn't so absolute. Willow erased that doubt. The gap is no longer a race. It's a separation between two different realities of computation. Classical systems operate step by step, tracing a single path. Quantum systems don't follow one path. They explore an entire landscape all at once. And here's where things start to feel uncomfortable. Willow isn't just faster. It's solving problems using a computational space so large that it seems impossible to fit inside the physical limits of the chip itself, or even inside the observable universe. A classical computer works like a disciplined thinker. One step, one decision, one path at a time. Even at incredible speeds, it is still fundamentally linear. A quantum computer is something else entirely. Instead of bits, it uses qubits. And qubits don't choose between 0 or 1. They exist as both at the same time. That state, called superposition, allows a quantum system to represent multiple possibilities simultaneously. But the real power comes when qubits become entangled. Because when that happens, the system doesn't just double its power. It grows exponentially. By the time you reach over 100 qubits, like Willow, the number of possible states becomes astronomically large, larger than the number of atoms in the observable universe. Let that sink in for a second. We now have a machine processing more possible states than there are atoms available to physically represent them. And that creates a paradox. If a classical computer performs work locally inside its hardware, then where is a quantum computer performing this vast amount of work? Inside the chip, that doesn't seem sufficient. Inside our universe, that also starts to feel questionable. This is where physics stops being comfortable and starts becoming philosophical. For decades, one idea has quietly existed in quantum physics, the many-worlds interpretation. The idea that every quantum event creates multiple branches of reality, where every possible outcome actually happens, just in different versions of the universe. Most people treat this like science fiction. But some physicists, including pioneers of quantum computing, take it very seriously because it offers an unsettling explanation to a very real problem. Where does quantum computation actually take place? If each possible state exists in its own branch of reality, then a quantum computer might not be calculating in one place. It might be distributing the computation across many branches simultaneously. Think of it like this. Imagine you had a problem so complex that solving it alone would take longer than the universe has existed. But the moment you ask the question, thousands, millions, even trillions of versions of you appear, each solving a different piece of the puzzle. Then somehow, all those answers merge into one. That's not science fiction anymore. That's one of the most coherent explanations for what quantum systems may be doing. And Willow forces that idea out of theory and into serious conversation. Because if the computational resources don't fit inside one universe, then maybe they are not coming from just one. Now, here's where it gets even stranger. Quantum computers don't just explore possibilities. They rely on something called interference. Different quantum states interact with each other, reinforcing correct outcomes and canceling out incorrect ones. It's how the system chooses the right answer. But interference implies interaction. And if those quantum states correspond to different branches of reality, then what exactly is interacting? In the many worlds framework, those branches aren't just abstract. They are real configurations of reality. And interference is the moment where those branches overlap just enough to influence each other. Not communication. Not a signal in the traditional sense. But something deeper, a shared computation across realities. Willow doesn't prove that we are receiving messages from another universe. It doesn't open portals or break space-time. But it may be doing something more subtle and more profound. It may be leveraging interactions between branches of reality to perform calculations that no single universe could sustain alone. And if that's true, then Willow isn't just a technological breakthrough. It's the first device in human history that might be touching the underlying structure of the multiverse. But Willow's most disturbing achievement may not be the 5-minute calculation. It may be what happened to the errors. Quantum computers are famously fragile. A tiny vibration, a trace of heat, a stray electromagnetic signal, any of these can disturb the qubits and ruin the calculation. This problem is called decoherence. And for years, it has been the wall standing between quantum computers as experimental devices and quantum computers as world-changing machines. Usually, when you add more qubits, you add more noise. More power, yes, but also more instability.